2, 1. Here we are. All right, I thought I'd start off by just introducing the course and saying a little bit about the course itself, because I'm the course coordinator, and I'll be taking you for 2 sessions, but obviously I'll be around to answer questions about the course throughout the semester. So the course, as you'll see, has a number of different assessment components. I've got 6 lectures, and they'll all be have some. Most of them will have material, which will be actually not all of them have material. Will be examining in the final exam, but essentially we'll have a final exam worth 50%. So we've dropped that back over the years from 70% to 50%. So the final exam, will be mostly focused upon Caroline's section, the power section done by Nick Burns, and it'll have a lengthy section from me. So my stuff, both in the lab and also in the lectures, will be in the final exam. And then there's a 20% section which is provided by Anna Johansson and also Deb Turnbull as part of their section of the course. They'll do a 20% online quiz sort of towards the end of the semester, just to break it up a bit. So you'll have, and then before that we've got a 30%. I think it was multi-choice, I remember last year, yeah. They might decide to modify it, but it'll be an online open book type quiz. And then the other component is a 30% assignment on psychometrics. So I think, so essentially in the past what we did was we had an assignment, we had any guys who did honours 2 years ago. The assessment, 30%, used to be like a statistical exercise where I'd give you a whole lot of stuff from this particular lecture, and then you'd then have to do a whole lot of calculations and work through a whole lot of problems, a bit like doing a maths assignment at school. Now, it's actually quite good. People used to go, oh my God, and they used to run to the maths centre, and the maths centre said, we don't know how to do this either. But you guys used to do very well. The average mark was like about 90%, so it was a good one in that way. But under APAC requirements, we have to teach you something about psychometrics, in other words, how to do and interpret psychometric tests, so how you get a particular test and how you analyse whether that test is of good quality. So understanding psychometrics is seen as a very important part of honours. It's a very funny thing because they treat everyone in honours as coming through as being pre-professional training, so all you guys are sort of have to be trained as if you're going on to be clinical psychologists or health psychologists or org psych. But of course many of you may wish to go on to do PhDs and work in research, a bit like me. So it's a little bit odd, but we have to do it so that your course remains accredited. So your 30% assignment will be more of an essay type assignment where you have to choose a particular psychometric instrument, which is sort of cool because if you're doing a thesis already, you might choose one of the ones you're doing for your thesis. And then you could write up a whole essay on that particular measure, which is good. So you can choose a particular measure. It could be a measure of autism. It could be one of behaviour. I have a whole lot of guidelines about which ones you're probably best to choose for this assignment. And I'll be posting the details of the assessment at the end of my lectures, probably the next sort of 2 weeks or so. And so you'll have about, I think, 5 or 6 weeks to put it all together, and you can ask me questions about whether the measure you've chosen to use is a good one. The main thing to avoid, as I'll say, is to avoid things like IQ tests, which is sort of huge. So you choose something that's a bit more manageable. Okay, so that will happen in a few weeks, and then a few weeks after that, with a bit of a break, you'll have the assignment from Deb and from Anna, and then you have plenty of time to prepare for the exam, which will be very much focused on particular parts of the course. So, as I said, the average of this course tends to be around about 80, and so most people do pretty well. So the average for the classes tends to be a first, so usually you should expect to do well. As I said, if you don't do well in this course, it's 12%, it's not fatal. You can the thesis, of course, worth 50% of your final mark, as Matt will tell you, and so occasionally we had people who had trouble in the exam, but it's not fatal if you get a very good thesis mark. Yep. That's right, yeah. That's good to remind me. I do a syllabus every year, so I actually give you a revision guide saying this is what you'll need to know specifically from my sections to revise. And so Caroline's section will be short answers usually, a couple of little short paragraphs. Nick's very similar. Mine tends to be short answers, things like, you know, what test would you use in this situation? What's chi-squared tests? You know, what's such and such? You know, interpret this regression output, that type of thing. So yeah, and I have some worked examples for you as well in the revision guide as well. So you'll know what it's all about. Yep.
And that's during the normal exam period?
Yes. Yeah. It'll be a Wayville exam. Yeah. Yeah. So I go down and find you guys in a little row. Yep. I do. The annual and Deb will have to decide when they want to run theirs, so it'll be later in the semester. The other one, I do have an exact date for the submission that's already been written, so I can't tell you off the top of my head when it is. It's probably about week 8 or something like that, but I can tell you at least that the time between me announcing it being available and the actual submission date is going to be about 6 weeks or something like that, so you'll have plenty of time to do it. Yeah. All right, well, today's session, first of two, this one's probably the slightly easy one. Next week is a bit of revision in this one, but next week, everyone, I've done this probably quite a few years, so some bits are more challenging than others, but everyone sort of eventually gets their head around the topics. And the other thing, of course, you'll learn in this course is how to use SPSS. So by tomorrow, at the end of the day, you'll have your first experience using SPSS. If you haven't used SPSS before, you've probably used R, some of you from Adelaide, yeah? Pardon? No, the actual stuff in the exam is going to be just generic interpretation of so it doesn't matter what format I use, so it'll be written in a very generic format. So you'll be learning how to use SPSS basically. So it's very easy to use, like Excel, and so you'll be thinking, I've never used it before. I'm going to the lab tomorrow. This is terrifying, but no, you won't take long to use it. I'll have a little half-page guide which you'll find, and I'll be roaming around tomorrow, helping you one-on-one how to do it. Basically involves opening a spreadsheet in Excel, cutting and pasting data into Excel, into SPSS. And one window in SPSS is all the data. And at the start it'll be blank, and you just go to the variable view window and you just name your variables, which will then pop up on the column totals in the data set. And then you can sort of put value labels in and you're ready to go. It's analyse, compare means, t-tests, correlations. It's all just button pressing and Windows-based design. So you'll find it's very important for you to know both SPSS and R. R is very good, I find, for modelling and so on, but for big data sets and very basic stuff, I find SPSS is a good package to use. And most employers out there will use SPSS. You work in government, in most areas they'll be using SPSS. And so you can walk in and say on your CV next year, I'm familiar with both R and SPSS, which most students will typically use. All right, so today what I'm going to do is look at analyses that can handle categorical data. So much of what you've probably done in the past has been to do with comparing means and things like that, so using metric data. So, interpreting measures of stress or scores on particular scales. But a lot of data out there, particularly what you encounter in government context and applied context, tends to be categorical in nature. So, for example, when I do a lot of work for government and a lot of reports. I've done dozens of reports, and most of them involve. You'll find this type of analysis, stuff that involves counts. So the government doesn't tend to be that interested in what people score on things. They want to know how many people smoke, how many people are coming in for services, how many people are doing this. Are there differences between Indigenous and non-Indigenous people and a whole range of outcome variables? It's often binary type data, count type data. A lot of industry stuff is a bit the same. And so you need statistical techniques that can handle that sort of data. Now, the ones which you're already familiar with would be, of course, chi-squared tests. You must have done chi-squared tests in the past. Well, we'll do a bit of a revision. There's a few little bits and little tricks for chi-squareds I'll teach you might not have known about before. So you do them really well. So we'll do a review of chi-squared tests. We'll also look at the kappa test for inter-rater reliability. One of the very important things you have to do as a psychologist, and even in research, particularly if doing qualitative research where you're trying to classify whether themes are treated the same way by different people, you want to see that there's a correspondence between ratings between two separate people. So, is this child on the spectrum? Has this person got clinical depression? one clinician will say no or yes, the other one says no or yes. How do we know there's a good level of inter-rater reliability? That's the Kappa test. The same thing with job interviews. You know, selection for clinical masters, they have little scales, and you want to know that they've all come up with the same sort of conclusions. So Kappa's very, very useful. Fisher exact test is a little test which you use when you can't use chi-squared test. Not sure if you've come across that one before, but it's used for 2x2 chi-squared designs. We'll come back to this in detail. Another important one is the binomial test. You're probably familiar with binomials from school and other studies where you calculate the binomial formula. But it's quite a useful test for studies of binary outcomes, used quite extensively in industry contexts, in quality control and those sorts of areas, picking up where the probability of certain events has changed over time. And I'll give you a few examples of how we use it. Proportion difference test, one of my favourites, so I use it all the time, which is essentially a bit like a t-test for proportions. It's, for example, are men more likely to smoke than women? Are men more likely to try marijuana than women? You know, simple proportion type tests. Are men more likely to, less likely to seek help for psychological problems, report sexual abuse, all that sort of stuff. That's proportion difference tests. I do dozens of these for government reports. You can use chi-squared as well, but proportion difference tests have a few advantages. Then the Poisson test. This is not about fish. This is a test which looks at picking up probability of flow of counts or events in certain standardised units. Like, for example, geographers might, agricultural scientists might look from satellite and say, are there more weeds or wildebeest or elephants in particular sectors in a particular park, or do the flow of customers per minute into a particular service delivery place, or that type of thing. I'll give you more examples when we get there. Flow of traffic is another one where you can use Poisson tests to see whether you've got a change in the flow of traffic. So if you end up working at, studying the psychology of consumer behaviour in supermarkets, the flow of people through supermarket aisles could be studied, for example, using Poisson tests to pick up whether you've got differences in the flow rates. And then we'll look at some non-parametric tests for related samples, the McNemar's test and Cochrane Q test, which I'm doing some work on that at the moment, actually, for a New South Wales government report, where it's really about whether the probability of a binary outcome changes over time. So a classic example is when you have a whole lot of people walking in and you test them on a particular ability, pass or fail. Most people don't pass. Time training, time 2, 50% pass. Time 3, 70% pass. It tells you whether the probability of the event's increased. The particular example I'm looking at is in relation to young Indigenous people, and they've got measures across waves or a longitudinal study on cultural connections, whether certain things are being done. So we're actually trying to capture whether there have been statistical changes in the probability of certain things happening. And so, and then having looked at that, we're then obviously doing some qual studies behind that. So that's the sort of type of thing that you can use this for. And of course, clinical outcomes as well, which I'll come to. But let's start with chi-squared tests. And as I was taught many years ago in economics, I often describe myself as a failed accountant. Not that I was failed, but I did accountancy and economics before I did psychology. So you'll see some very strange economic type publications with graphs and demand curves and a cage in my publications. And I work with the SA Centre of Economic Studies a lot. Two types of chi-squared tests. There's what's called the one-way chi-squared test, we used to call it, and also called the goodness of fit test. And then there's the contingency table, or what we sometimes call the two-way chi-squared test. That's the one you'd probably be familiar with from last year and previous years. Now, the goodness of fit test essentially tests whether an observed distribution of scores matches the distribution you might expect by chance, which is why it's called the goodness of fit test. It's really how the observed distribution of scores, which usually looks a bit like a New York skyline, how it maps what you might expect by chance, which is usually a rectangular distribution. Everything's the same. Classic example might be, for example, you've got, you think, is there something I have actually done before, and my student Luke Snyder did his PhD on looking at lateralisation in canines. We actually studied greyhounds running around tracks and whether certain tracks had a high number of wins, testing out whether left and right paw dogs ran different ways and different starting positions, that sort of stuff. But here's an example. Often the question that's raised, do horses win more like to win on the rail, or do they more like to win out on the starting out wide? And so you could test that. If you had 8 races, you had sort of 10 races with 8 horses, you'd expect on average 10 wins from each of the 8 tracks. You had 5 photocopiers in the library. I'm not sure people use photocopiers as much as they used to. I think people print stuff out these days probably more. In my day it was get like radiation sickness, just endless sort of copying sort of articles endlessly. Everything was just based on the shelves, walking around with this pile of books and just sort of skin changing colour. Photocopying. Or 3 lanes or aisles in the supermarket. Are some lanes used more than others? They do study this. They put all the sweets in the middle if they think that's where all the people are going to walk. So basically, you had sort of 300 people tracked into a supermarket and the 3 middle aisles. If it made no difference, it'd just be 100, 100, 100 going down the 3 aisles. Same if 500 students walked into the library, you'd see 100 using each of the copiers. So the distribution is rectangular. Damn, I should put that in my pocket. Never mind. That should need it. So basically, rectangular distribution. So if you had aisles in a supermarket, it should just look like that. Same number of people in all 3 of the aisles or the racetracks. Yes, the one in the other lecture, I think it kept on falling off. Where you put it. Okay. So here's an example. So you've got 3 vending machines. Do some people use some of these vending machines more than others? Universities have many experiments over the years with different food outlets and vending machines. They had like a little mini Pizza Hut there about 10 years ago, and it lasted for a little while, and then it disappeared. That was 15 years ago, maybe. Anyway, so if you've got 3 vending machines, 120 people, you expect, on average, by chance, only 40 people would use each of those 3 vending machines. That's what you expect by chance. That's the expected. But of course, the observations show that you don't get that. So you've got 45 using 1, 20 using 2. It differs from what you expect by chance. And so what you get is the sort of pattern of distributional dissimilarity. So you get a pattern like this, where you can see that the pattern of observed doesn't match what you expect by chance, which is always equal, 40. And the question, of course, is that a significant difference? Does the observed frequency distribution differ significantly from what you expect by chance? Of course, that's what the chi-squared test, goodness of fit test, looks at. The formula is essentially, you just take the observed frequencies. So you've got the observed frequencies, of course, here. You basically take that from that, square the differences, divide by the expected frequency, that's the one by chance, and then add them up, and that's your chi-squared value. And it becomes very clear when you see it in the spreadsheet format. So here's the formula. So it's the observed frequencies, take the expected frequencies, or the chance frequencies, and you square those differences, divide each one by the expected frequency, or the chance frequency, which is a 40, and add them all up, and that's your chi-squared value. And so it's very clear when you see it in the spreadsheet. This is how I do lots of these on the back of an envelope or a bit of paper, because you often have a situation where I don't have the data, or you're marking a thesis or reading a paper and you go, no, that's not right. And so you get a bit sad, I know. I get the figures out and you can calculate it manually. So basically you've got the observed frequencies here, expected frequencies here. You take the difference, 45 take 40, and you square those differences, and then you divide each by the expected frequency. 25 divided by 40, 0.63, minus 20, actually 400 divided by 40 is 10. 225 by 40, 5.63, add them all up. That's your chi-squared value of 16.26, which is your obtained test value. That's your obtained value of chi-squared. Now, is that significant? How do we know if it's significant? Anyone?
It's closer to 1, it's less significant.
That's right, yep. So basically what we do is we compare the obtained value with a critical value. Based upon and the critical value is based upon the probability level you want to test at, and also the number of degrees of freedom. So in the back of any textbook, or you go onto Google and search for critical values of chi-squared, you'll go, right, 0.05, go along. You won't have to go very far in this case because you've only got 2 degrees of freedom. Degrees of freedom in a one-way or goodness of fit test is a number of levels take 1. So if you've got 3 machines, take 1, you've got 2 degrees of freedom. And so you go along on your table, 2 degrees of freedom for 5% probability, critical value, I think it's 5.99. You sort of remember them after a while. I think for 1 degree of freedom it's 3.83 or something like that. I can't remember the next one. And then if your value is greater than that, then your result is significant. In this case, of course, it's very significant. It's heaps bigger than the value. And so what we conclude is the observed distribution of scores differs significantly from what would be expected by chance. So that's how you interpret a one-way goodness of fit test. So some machines are disproportionately underused or overused. If it were the horse racing example, you'd be saying it seems that horses which start on the outside have a disproportionate number of wins, or something like that. And what we were looking at in that particular study was whether, I think, is it right, left-pawed dogs might have been, or right-pawed dogs, whether they win on the outside, so because they're looking back over that side when they're going along. That's why people in America drive on the right-hand side. The old wagons, you look over that way at the oxen. Yeah, supposedly. So, good. So that's the how you interpret it. So a little bit different from the conventional chi-square, the 2x2s, but there are some similarities. Now the two-way chi-square, of course, is the one which looks at the association between 2 categorical or ordinal variables. It's what we call a test of independence or association. It's a bit like correlations or a test of association. And so if the variables are related, then we describe them as being interdependent. If they're unrelated, there's no effect, we say they're independent. For example, is gender related to the preference to your most preferred form of ice cream? Is a person's SES and ethnic group related? Are smokers more likely to be drinkers? Are university students more likely to report Jedi on the census? Probably true, yeah, I think. Are they more likely to listen to Triple J? Probably, yeah. So it looks a little bit like this one here. So you've got these figures here are, of course, the observed figures. That's the actual counts. That's the number of men who used machine 1, number of women who used machine 2, for example. And you add those up to get the row totals. So if you're doing one of these by hand, I've done a lot of these because you often get data, you haven't got the data to do it in SPSS. So you add up the row totals, get the grand total here, and you have column totals here. So this is the total number of machine 1, machine 2, machine 3, so on. That's all you need to do the chi-squared calculation. So to calculate chi-squared tests, you know what the observed frequencies are. They're all given here. The expected frequencies are given by this formula here. It's the row total divided by the grand total times the column total. So we go back here. If we take the cell here, it would be the row total, 180, divided by the grand total times the column total corresponding to that one, gives you the expected frequency here. This one here, row total, 110 divided by grand total, 290 times 80, gets you that one there. It's a bit like playing battleships. It's just the coordinates, that correspond to that particular one, or Minesweeper, or whichever one. So basically, you just calculate, you essentially just do the same thing. Once you've calculated those respective frequencies, you put them into the spreadsheet, and you just calculate the chi-squared the same way. And so I haven't got a full worked example here, but I do have one on the handout. So we go to the Word document, back up to here. Make this a little bit bigger for you. Yeah, you can sort of see here, there's the expected frequencies. You take the difference, you square them. There's divide by the expected frequency for every row. And you get a chi-squared value of 18.69. Yep. And now with two-way chi-squared tests, the degrees of freedom is calculated slightly differently. So I'll just do it. So these are all the actual calculations. So we compare the critical value. Now, the critical value for a two-way chi-squared test is number of rows take 1 times number of columns take 1. And so obviously number of rows here was 2. 2 take 1 is 1. 3 take 1 is 2, so it's 2. 5.99 would be the critical value of chi-squared. Your value is huge, therefore the two variables are associated, they're interdependent or related. So gender and choice of vending machine is related. Now, pardon? Yep.
Critical value depends on the p-value that if you
That's right.
p-value is 0.05, it would be 5.99.
That's right. You're right, yes. So if you, most times we tend to use 0.05, but you're right. So in a table, you could choose to be stricter and go for 0.01, in which case you'd need a much bigger critical value of chi-squared to be exceeded. But in this case, you'd still be significant because it's such a huge test value of 18. So, yeah. A few points to know about chi-squared. No more than 25% of the cells can have a minimum expected frequency less than 5. So when you're doing that row total divided by grand total times column total, and you get a value less than 5, and that happens quite a few times, and SPSS will tell you, it'll say you've got 50% of your cells have a minimum expected frequency less than 5, and your test is invalid. You can't use chi-squared. And so what usually has to happen then, you have to sort of collapse the categories. So if you're doing studies of, for example, it will happen, for example, in Australia when you're studying, say, nationality. Australia's a very tough place to study nationality. We just don't have very good numbers across different groups. You'll get, you do a population survey and you'll go Aussies, biggest group, second big group, UK, New Zealand, and then it's like 3% Greek, 3% Italian, 3% Vietnamese, and you go, okay, what? So then you have to look at it and go, this used to be on the questions I used to give you guys in the assignment, and you have to try and make reasonable calls on what you can group together. You might sort of make sense maybe to have Europeans as a group, maybe, or non-UK Europeans. You might have North America possibly, but it gets much harder when you get to Asia because they're such different countries. So people end up having an other category and it becomes a bit meaningless. So that's the sort of situation can arise. Religion's not so bad. You could probably put the Christians together and have Islam or something separate, something like that. That makes sense, but otherwise not so easy. Occasionally there's ways you can get around it with using other tests. Kolmogorov-Smirnov test can be used occasionally. Sounds like a drinking game, as I say, on a Russian battleship. It's a bit sort of weird name. But yeah, it can be used occasionally. There are effect size measures for chi-squared as well. So, for example, for the 2x2 chi-squared, you can use the phi statistic, this one here. So if you want to impress people in your thesis, do a 2x2 chi-squared. So that's the 2x2 design. That's mathematically equivalent to calculating a correlation with two binary variables. It's quite a conservative sort of value. So the phi statistic can be used. For any other type of chi-squared design, you can use Cramer's V. So that they're your effect size measures. And one of the other tricky things about chi-squared is that, particularly when you get like a 4x3 table or something like that, you've got all these percentages. What you have to do is do a table in your thesis or your report. So you might have, four different levels of SES, and you might have some other variable down the side, and all these numbers, and you've got a significant chi-squared value. How do you interpret the result? Sometimes it's fairly obvious. You can just sort of look at the smaller ones. You can just look at the effect and plot it, and it's obvious that women prefer something more than men or something like that. The other way you can do it is using what are called standardised residuals. In SPSS, you'll see them tomorrow. You'll see it pop up. What you can do is SPSS, for every cell in your design, say 4x3, it will give you these things called standardised residuals, which essentially states a standardised measure of the difference between the observed frequency and the expected frequency, which obviously drives the size of the chi-squared value. So the bigger those differences in each cell, as you know from the calculation, the bigger the chi-squared value. And so the standardised residuals, if they're really big in a given cell, that tells you that particular cell is very influential in the overall result. And so what you can do is to say inspection of standardised residuals indicated that this result appears to be the result of women doing this, or men doing this, or this particular group doing such and such. That tells you which of those cells is most influential in the result. And so values of about 2, whether at minus or plus, are ones which are very indicative of a strong effect. It's a bit like interpreting a t-test result or a z-test result. 2 is big. Any sort of standardised value of 2, standardised units is big. And that's how you can do it. So inspection of standardised residuals is a way of doing it. I got taught this by ABS statistician when I was working, doing some government work. He said, this guy, he's a bit like a truckie. He said, mate, just use your standardised residuals for interpret the result. All right, so ever since then I've been, doing the standardised residuals. Now to do it in chi-squared, you do it through, you just go into Analyze, Statistics, Crosstabs, and then one of the options under the Statistics tab will be chi-squared. And what you usually do, as I'll say in the handouts tomorrow, you request the cell values and percentages so you can actually see what's actually happening in the design. It was invented by Pearson because it is actually related to the correlation coefficient. As I said, the 2x2 chi-squared is basically a correlation coefficient for binary variables. You can do a proof to show that. So Pearson's chi-squared value will come up as the test statistic in SPSS. It'll have degrees of freedom and it'll give you a probability value. So you won't have to worry about looking up critical values. It'll just be there, like an NR as well. You'll just get the p-value and you'll look to see whether it's less than 0.05. If it's a 2x2 design, it will also automatically produce the Fisher exact probability as well, which we'll come to fairly soon. So this is how you report it in your thesis. This is a standard APA format. You usually italicise the chi-squared value. Actually, I think you italicise that one as well too, and that one, the n, the p-value. So using standard reporting methods, you do it like that, but you can actually report exact probabilities too. I'd say 10 years ago everyone was doing standard probabilities, but now everyone's doing p equals 0.0035 and so on now. So the general rule is you stick with one method. So if in your thesis you're doing reporting exact probabilities, do so consistently, but don't mix up the methods. I still tend to do the standard method, yeah. I provide all the effect size and so on. So the way in which you interpret it and write, you say there was a significant association between gender and choice of machine, comma, and then you put that bit here at the top. That's a standardised way to write it up. And then you then interpret the results. If you can, from the graph or little table you presented, you say a greater proportion of females preferred machine 1, whereas males preferred machine 3. Or you say inspection of standardised residuals suggested that blah, blah, blah was causing the effect. That's how you do it. Any questions? That make sense? Yeah. Okay, let's move on to the next test, the Kappa test. So this is one used to examine inter-rater reliability. Even though it's largely used in quantitative research, often clinical comparisons, you guys doing qual theses, particularly those doing thematic analysis, might have opportunities to use it because you want to see if your themes are classified the same way. And you might have, about 50 to 100 blocks of text to themes, and you then give them to two independent raters who then go, yes, that's... let's say it's a study of racism, for example. I'm not sure I was working with Martha, and you said racist, not racist, or offensive, and then you might, each rater sort of does a rating. And then you hopefully the two raters are consistent in their interpretation of the theme, so you can use it in qualitative analysis. Often when you try and publish, in your thesis they'll ask you how did you test for inter-rater reliability, how did you ascertain. What a lot of people do is simply give the whole lot of themes to other people and then say, well, my mate classified 90% the same way. You can do it that way too, but Kappa is often a good way to do it. Okay, so for example, 2 clinical psychologists are asked to assess 50 clients. Do they have depression or do they not? Another example, on the org site, 30 job applicants are rated as suitable by 2 different interviewers. For the clinical masters, like about 50 or something, people get, yep.
Sorry, does that mean they're doing 30, the same 30?
That's right, yeah. So the basic idea is you've got the same group of people being assessed independently by 2 different people, yeah, or classification systems. So you can see how this is useful for a number of, for example, diagnoses of disorders that require two independent classifications. So for example, for children, autism, it's got to be paediatrician classification and an independent psychologist saying before its diagnosis is confirmed. There's quite a few things like that. And you want to be confident that, in fact, there is a correspondence between the 2 sets of raters. So how do you do it? Well, the data looks like this. You essentially got yes and no type data, which might be something bad. Yes, the bad thing is present, the depression's present, or disorder is present. Or it might be you have passed, you are suitable. Both people agree, we want this person in the clinical masters or health masters or something, Now, the key bit here is this diagonal here. This is the agreement diagonal. And so the total number there is 100, and you can see there are 45 plus 20 where they both agreed. 45 where they both said no, 20 where they both said yes. And so the proportion of agreement, of course, is 0.65. 65% of cases there is agreement across the diagonal. To calculate Kappa values, you use this formula here. PO does not mean post office or best off or anything like that. It's rude like that. It is actually probability of observed frequencies, which is essentially probability of agreement observed across here. And the trick now is to calculate the proportion expected by chance across that diagonal. So that bit's easy. It's 0.65, straightforward. You've got it. How do you calculate this bit here? Well, how you do it, it's actually in the handout. I've got, because it's a bit hard to do this all in. So go to the actual handout. So you have these notes to look at. What you basically see, I've reproduced the data here. So you've got, I think this is the same. Is it the same example? Might be a slightly different example. Actually, I think I might have a. Wait a second. So I've got the different example. That's right. Here's the actual example. So, 50 cadets applied for the Air Force and were assessed by 2 evaluators. 18% were considered fails or no's by both raters. 24 were considered a yes from both. So therefore 0.66, 66% agreement. And on 17 they disagreed. So 34% there was disagreement. So we know straight away We'll now go to the handout, and I'll come back to the PowerPoint. You can see that, yeah, the 9 out of 50 or 18%, no, they agreed. 48%, yes, they agreed. Add those two up, you've got 0.66. 66% agreement. 0.66 is your PO, your proportion observed agreement. What you need now is the proportion of agreement expected by chance. And to do that, you just use the basic independence formula. Those of you call your probability, I guess, from other studies. It's basically, what's the probability of the two of getting no nodes by chance? Well, Rater 1 gave 38% of no's. Rater 2 gave 32% of no's. So the probability of them both saying the A intersection B by chance is just the two multiplied together. So the probability of two no's by chance is the probability of Rater 1 saying no, which is 0.38, times 0.32. And then do the same thing for yes. Rater 1 in general says yes to 62%. Rater 2 says 68% yes. Multiply those two together. The probability of getting them both saying yes by chance is the product of those two. And we add those together, that's your probability expected by chance. You never have to calculate this yourself because it'll all be done on a computer, but just so you understand the basic logic of how it's done. If you're ever stuck on a desert island saying, I have to do a kappa, then this is how you do it. Yeah. So basically, it looks like this. So you've got the observed agreement, 0.66. That's easy. And then the PE, I've already done all this, convert to proportions. And so the probability of them just agreeing by chance is 0.62 times 0.68, which is 0.42. Probability of them both saying no. Once again, A intersection B, probability of both is 0.12. Add those together, it's 0.54. So that's a probability expected by chance. And all we do now is to slot that back into the formula, which is that one. And there we are. There's your kappa value. So this is one of the assignment. One of the things you used to do with the assignment a couple of years ago. Just calculate a kappa value like this, and so it comes out at 0.26. Now kappa is interpreted a little bit like correlation coefficient. 0.26 is not, or it's even worse. So 0.26 is not very high. So you would not be very happy if your inter-rater reliability was 0.26 for your study or for your clinical trial. It's pretty bad. A good value is about 0.5. 0.70 is very good, but 0.3 is pretty crappy. It's not very good. It can go negative as well. K tends to be very, just a general sort of, number of years ago, we worked at K tends to be a bit unreliable when the base rate of phenomenon is very rare or very high. So if you're looking to go out in the general population, try and say this person's got schizophrenia, this person hasn't, it's not going to be very reliable because it's so few people who've got schizophrenia in the population. It's very low base rate. Or if you went out there and said, I want to, have inter-rater reliability on how many people have got two eyes. Very few people have eye injuries and lost an eye, and so you end up sort of not being able to do a proper kappa. It wouldn't be very reliable. Kappa is done just in the crosstabs function in SPSS, so you just go analyse, the central column, statistics, crosstabs, and you just request a kappa. So you'll have two columns of data with the two sets of raters, Rater 1, Rater 2. You just put one across in the box, another one across in the box, go in, statistics, request kappa. And then you're right, you've got your kappa value. And it has a significance test, so you can find out if your kappa value is significant as well, in addition to knowing whether it's of a reasonable size. So it can have a negative value, which is very evil if it happens, but that's something seriously wrong if you've got negative kappa value. Okay, any questions about the kappa test? Yeah, as I said, you'll be able to do it on SPSS, but that gives you a sense of how the basic logic underlying the test. Okay, the Fisher Exact test, it's not one you want to attempt manually. The formula for this has got like 2 lines of factorials. I actually got it in the handout. I think it's sort of, most calculators sort of start smoking when you try and do it. You use this one when the 2 by 2 chi-squared test is invalid. So you use this particular test when you've got very small samples and you go to calculate your minimum expected frequency and it's really small. You're getting violations of the assumptions, and so you use a 2 by 2 chi-squared test instead when you've got this. Sorry, so you use 2 by 2 Fisher Exact test instead. The good thing about this test is that it's automatically reported every time you run a chi-squared design in SPSS with a 2 by 2 design. So if you run you run 2 variables, both of which have got 2 levels, then you get the Fisher Exact automatically. And so you can look down and go, my chi-squared test is invalid, but then you've got the Fisher Exact to report instead. So that's all good. Only difference here is the Fisher Exact test doesn't have an actual test score. So you don't report, for example, a chi-squared value or any sort of value. You just report probability. You just say there was significant association between the 2 variables, Fisher Exact, comma, p less than 0.05. The Fisher Exact test should not be confused with the Fisher least significant difference test, also known as the Fisher LSD test, which is available as a standard test and over for post-hoc tests, which is mathematically equivalent to the planned comparisons method for comparing groups in ANOVA. So when you do ANOVA comparisons, you have your overall F or group difference. You want to do post-hoc tests. One method you can use is called planned comparisons, but there's a test called Fisher LSD test, which is mathematically equivalent. That's the most generous of all the post-hoc tests you can select. A lot of people tend to use things like Bonferroni tests and other ones like that when they do their comparisons. But Fisher LSD is the most commonly used, but not to be confused with Fisher Exact tests, which is a test of association used instead of chi-squared. I've had reviewers get that wrong. Yeah, they've picked up, that's not, what's that? No. But otherwise, the interpretation is the same as chi-squared, 2-way chi-squared. Okay, binomial tests. These are essentially used to test for binary outcomes. Most commonly, things like left and right, good versus bad, clinical versus non-clinical, left versus right-handers, all those sorts of things. You could do it with gender as well for binary gender in animals, those sorts of things, in populations, like you're studying plants. Does the probability obtained for one event differ from what's expected by chance? That's fundamentally the question you're trying to answer. So sort of examples include, I'll get to those in a minute. You usually encounter this as a Z test or approximation. And basically, it's tested like this. You're looking, the X is the number of right-hand turns, for example, you observe. So in a particular binary outcome, you have an observed number of outcomes based upon what one of the binary alternatives has as an observed value. And then there's a value which indicates the number you expect by chance. So the common one, of course, is tossing a coin. Is my coin biased? I throw the coin up 100 times and I get 60 heads. 60 heads is the X. That's the number of obtained binary outcome. I could do it tails as well, but I'm going to choose heads. The mean number you expect by chance, of course, is 50 out of 100. That's the expected number. Only thing you don't know is, of course, the standard error to do the test, and that's a simple formula. So X is the observations of the binary outcome you've chosen to test for. That's the number you expect by chance. So, for example, you could test whether the Australian cricket captain is better than chance at throwing the coin and winning a toss. You could poor Ricky Ponting, he's got it all wrong. Used to lose the toss all the time. So you could actually work out if a particular captain had to do a toss 100 times, you expect him to win it 50 times. If he got only 40, you might say, he's not very lucky with winning a toss. So that's the sort of fundamentally important questions you could answer if you use the right a binomial test. The standard error, which you need for the calculation, is very simple. It's simply the number of tosses or the number of trials times by the probability of the event as expected. So for coin tossing, of course, that's 0.5. So this would be the square root of 100 tosses times 0.5 times 0.5. One take 0.5. One. Yep. I'll do an example. So the observed count is very easy. You got that? The speculative mean is simply the number of trials you've conducted times the probability of the event, the long-term or expected probability of that event by chance. And of course, in most situations, a binomial test, it's 50-50, it's 0.5. So for 100 people, the mean number expected will be 50 for that particular binary outcome. So for example, do people tend to ignore a stop sign? This is a bit of a dodgy example, but the next one's probably a bit better. 100 people are observed to approach the sign. There's people in the road traffic unit out there observing. 70 ignored the sign. Is 70 unlikely to be observed by chance? Assuming this is a binary outcome, you either go through it or you stop. Well, 70 is what you obtained. If it's a binary outcome by chance, then 50-50, so 70 take 50, divided by the square root of 100 trials or observations times 0.5, 0.5, 4, which is very significant, which suggests that people are not seeing the sign. It's just as likely, they're more likely to actually go through it and ignore it because it's behind the tree or something like that, than to stop. Another example is drug use increasing in the office. Here's one where the probability of the event is not 50-50. Previous testing suggests that 5% of people come up testing positive for drugs in the office. We used to have Michael White come in to do a current issues talk for you guys. He's talking about drug testing in transport. It's a little bit dodgy because, as he said, there's no evidence much that having a small trace of meth or various other things in your system has any effect on your driving, but it's a backdoor way of getting testing for illegal drugs. It actually has no effects. But people do it in the workplace too. I mean, it's important probably in transport and aeronautics and those sort of things because people will be at risk. But basically, a new test was conducted of 200 people in the workplace and found 10% came up, 20 people came up as positive on a drug test. Has the level increased significantly? Well, 20 is the number you observed. What did you expect by chance? Well, the old rate was 5% and you've tested 200 people. So 5% times 200 people, that's what you'd expect by chance. That's the new rate number you've got from the 200. And you slot in the 0.05, which is the standard mean rate, take times 1, take 0.05 times 200, take the square root. Comes out to that. 3.24, which would be very significant. So any Z value greater than 1.96 is significant. And so this tells you that the binary outcome, namely detection of drugs, is much higher than the established 5% rate you've seen in the past. So drug use or detection seems to have increased in the office. Now, I had some other examples here too. I'll just go back. I must have missed that slide. I'll show you. Yeah, maybe I didn't. Yeah, a few other examples of. Let's go back to where we were. Yeah, other examples of binomial tests. My student Luke Snyder was doing studies of lateralisation in dogs. He wanted to work out whether the dogs are right-pawed or left-pawed. And so the way in which you do that is you fill up a Kong or this sort of tube with meat and you half seal it. And the dog then is presented with it. And so doggy goes up and which paw the dog used to hold the Kong down and to chew out the meat, to sort of pull it out of the food is how you test for paw preference. And so you do the first trial, right paw used, second paw, hopefully in the right trial. And so if you do 100 trials and you get 70 and 80 right paw usages, you get pretty confident that that dog has got a right preference. Another way to do it is leaping over a hurdle. The right paw dogs will lead with the right paw, and so you're doing some time-lapse studies looking at dogs jumping and the paws being what paw they lead with. And there's a few other ones as well. You can do the same sort of thing with which hand people prefer to use for certain things. So for babies, for example, you can see which hand they lead with for certain types of grabbing behaviour and so on. It's also very commonly used, as I mentioned, in quality control studies, a bit like the drug study, where you might say, well, in a batch of X number of goods which are produced, like might be light bulbs, is always the example I used to give in economics, you might expect 2% of the batch to come out faulty. Or it might be in a count of fruit quality. You're doing, you're sorting fruit or expensive fruit. 2% have blight or are not fit for sale. You can then use this type of test to ascertain whether there's been an increase in the percentage of bad batches. So if it goes from 2 per 100 to say 5 per 100, the binomial test, exactly like we just calculated for the example of the drugs, is used to detect whether you've got increases in defect rates. So the binomial test, very, very useful for batch control and that type of testing. Okay, proportion difference test. Getting closer to your coffee. Yeah. This one's a bit like a t-test for proportions, and it's one of the most useful tests, I think, and one I probably use the most after chi-squared. This is a parametric test which examines whether two samples are drawn from populations with the same proportions of a given characteristic, or whether it's different. For example, are males more likely to smoke or gamble than females? Are port supporters more likely to drive Fords than crow supporters? It's a pretty important question. Yeah, always have a silly example so you remember. Is there more clinical depression amongst women than men? That's a common study one. And of course, another important one, are men less likely to seek help for psychological problems? That's a classic example. Public health surveys will often ask questions about all these sorts of things and use chi-squared or proportion difference test to ascertain whether those two proportions are different. So why use the proportion difference test? Well, it's easy to interpret. You get a nice Z-score, a bit like a t-test, and you can also calculate a confidence interval around it, like a 95% confidence interval, like an error margin around the value too. And that's in some statistical reporting, people like that. So you can do that with it. Okay, let's have a look how you do it. It's very easy to do. The formula looks a bit complex, but it's very simple. Proportional, that's simply just the proportion in one group. That's the proportion in the other group. And then the p hat is just the overall proportion for the sample as a whole. And then the n's are simply the number in each of the two sample groups. So here we go as an example. Next slide. Don't worry about that. So you've got 50 males, so that's the n for males. N1 is 50. N2, females are 70. That's easy. That's the two sample groups. What's the proportion of smoking in males? Well, that's here it is. It's 0.3, 15 out of 50. That's your P1. Your P2 is 0.14. The overall proportion of smoking is simply, how many smokers we've got? 15 plus 10 is 25. 25 over the whole sample is 0.21. So the P hat, or P prime, is 0.21. So you've got all the figures you need to do your calculation, just from that. And you just slot those into the formula. So 0.3 of males smoking, take 0.14 of female smoking, divide by P prime, overall proportion, times 1 take P prime, times 1 over 50, number of males, plus 1 over 70, number of females. When you do it manually, you've got to get your brackets right on the calculator, do your BODMAS, what you call it, get it right. And so it's 0.16 divided by that, and then 2.12. And so, as is the rule with Z-test, anything over 1.96 will be significant. And so quite clearly the two proportions are different. We'd say that men are more likely to smoke than women. The more formal statistical interpretation of it would be that they do not appear to belong to the same population where the proportion is the same. Men and women seem to belong to populations where the mean smoking rate are different. A bit like you do for t-tests, independent samples t-tests. So that's the proportion difference test. As I said, a very, very useful test to use. Make sense? Yeah. And when you report it, you just say there was a significant difference between the smoking rates for males and females. You might in brackets say 30%, 14% for females, comma, Z equals 2.12, comma, P less than 0.05. So when you actually write it up in an article, you do it like that. So you do Z equals 2.12, P less than 0.05. A bit like you write up a Z test, you just report the proportion difference test hidden behind there we are. There we are. Not the most elegant writing, but okay, Poisson tests. Pretty simple one. This one tests the probability of event flow in equal sampling units, so or single events, or X events per time. Makes sense. I've got some silly examples. Here we are. If an average of 2 customers arrive per minute at the bank, what's the likelihood of getting 4? Now, the reason people might ask questions like this is to do with how many staff do you put on at certain times, and so there's been studies where people have looked at a lot of commercial operations will look at customer flow and looking at in studies of exchanges, look at number of information flow. They try and work out how many people need to be on the phones or sort of doing a service desk to meet the flows at different times of the day, those sorts of things. You can look at whether the flow differs depending upon the type of day using a Poisson type test. It's a very silly example. If leprosy, you found 1 per square kilometre in Burnside, what's the chance of getting 3 any 1 square kilometre? If 3 cars pass a spot at the end on the road, so the counters put down their little black counter things, and then boom, they're recording cars going over it. What's the likelihood of getting a rate of 4? So the council, for example, thinks the people in Unley area. People aren't there complaining about the traffic moving through, all these people taking shortcuts. There's more traffic. So if they get a rate of 4 when the average has been 3, is that a significant increase in the number of cars going past every minute? Poisson test can answer that question. Poisson tests can also be used to sort of measure the frequency of things within areas. So, for example, it was actually originally used in World War II to map the hits by the doodle bugs, the V-1 rockets. The Germans in 1943 or 4 were firing the V-1 rockets, the doodle bugs, over the English Channel. Those little flying bombs. They'd sort of come over London and then stop and then crash. They were mapping the distribution of hits across London using sort of standardised units of area, and they were able to. It did follow a Poisson distribution. The similar things if you're studying, from the air, the animals, for example, how many elephants from a certain area, or weeds, for example, in weed infestation studies in geography, agricultural science, they might look for the presence of certain trees or weeds and so on. Similar type of analysis could be used if you use standardised sort of units of measurement. I think typically in that type of analysis you use hexagonal patterns because you want to have because hexes have they're tessellated, they're sort of they all have no gaps between them when it comes to mapping the area. So to calculate Poisson values, it's given by this formula here. E, of course, is the magic number. Yep. 1 plus 1 over n to the n, limit of 1 plus 1 over n to the n, which is about 2.77, I think, or something like that. Raised to the minus mu. Mu is just like the standard rate of something happening. So that's the 3 cars going through, 3 cars passing someone's house in Burnside or in Unley. That's the standard average flow rate, or it's the 3 customers who come per minute to the bank. or the 3 elephants in the area. And then the X is the actual number you've observed, which you're comparing with the mean rate of flow or incidence which you've seen in the past. Yeah? We used to use Poisson many years ago when I was doing learning behaviour with a class actually about this size. Learning behaviour used to be this big back in 08 and earlier, and we used to have the zoo prac. And you guys were off sort of the clipboards off at the zoo studying animals, and one of the things you guys used to do is to map out the enclosures into equal units and then work out, use Poisson to measure whether the chimpanzees use certain parts of the enclosure more than others. It's one sad thing about having very big classes, you can't sort of do some of these things, but students used to map out the areas and then sort of work out Poisson probabilities and work out where the chimps and all the giraffes in the case would spend more of their time. So 5 cars pass through a point in, I always call it only a ghetto where I live, I'm not going to get trapped in there, every 5 minutes. Too many cars, yeah, you probably know those guys. Another road is blocked off. Too many cars going through. And so the council evaluates the change. Over a 2-week period, they observed that only 1 car passes through every 5 minutes. And in the past, it used to be 5, every 5 minutes. Now it's gone down to 1. Is that a significant change in flow? So you pop those figures into the formula. So e to the minus 5, which is the old mean rate, times the mean rate raised to the x, which is the new rate of 1 per minute, divided by factorial value of 1, which is just 1. Factorial, of course, is 5 factorial, of course, is 5 times 4 times 3 times 2 times 1. And probability comes out at 0.3. Now, strictly speaking, when you do these types of tests, you test for the probability, like binomials as well, you test for the probability of 1 and fewer. So you test for the probability of getting only 1 car passing per minute, and you'd also test for 0 as well to work out the final test probability. But this just gives you an exercise to show you how you do it for testing for a rate of 1 as compared with a mean of 5. As I said, you don't need to you're not going to be tested on this formula in an exam or anything like that, just to be aware of the actual test so that in the future you're thinking, I've got a situation where I want to test changes in flow. Am I getting more customers into this service or per minute or some particular situation? Hopefully you might remember this particular test has been the one you use. And of course, Poisson can be used as a form of regression as well. There are often Poisson forms of regression. So if you see that pop up, you'll know what a type of Poisson probability is all about. Okay, and the final one, you're very close to coffee now. Looking at repeated measures in categorical data analysis. So this one here, there's 2 tests. The Cochrane's Q is usually the one you do first, which is a bit like an ANOVA for categorical data. And then you've got the McNemar's test. Now it looks a bit like this. A group of people are asked to indicate what flavours of ice cream they like, and it's where you can choose more than one type of ice cream. So I say to you, right, vanilla, chocolate, strawberry, which ones do you like? And you can tick all 3 if you wanted to. It's not most preferred, which ones do you like? And say, or which countries would you like to visit? And you go tick, 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 tick. You can tick lots of them. People entering a training program. You can think of all those sort of reality TV shows. 50 people, they don't, first test, not very many people pass at the first testing point. And then the training is conducted, and then after a certain point, it might be athletics training, it could be swimming speeds, it could be anything. And then more people out of the group pass or reach a certain benchmark at time 2, even more at time 3. Where have you observed significant improvement? How do you test for that? Do clients in the CBT program get better over time? Now, you can't use a chi-squared test for this because you can't do sort of like a time by outcome chi-squared because the data is measured at different points in time. It's not independent. So chi-squared, the data has to be independent. Here you've got the same group of people being asked about 3 types of ice creams, the same people being given the rating, so your data is not independent. So for example here, see, person 5 has answered 3 questions. So you can't do a chi-square with a variable saying this is the person's ID times preference, because it's 3 separate variables. It's going to have 3 separate columns in the data set, 0, 1, 0, 1, indicating do you like that type of ice cream. You can't do chi-squared. It's not independent data. Another example, as the training proceeds, more and more people pass the test. At first, only 1 person out of 5 passes. Over time, it ends up being 4 out of 5. Another example? Yeah. Or people come in clinically depressed to your practice. They're all assessed as being clinically depressed at time 1 at intake. You then start the CBT program or your clinical treatment for 4 weeks. You test them again, and a couple of people, or 3 people now are not clinical. And then you run another 4 weeks, and then they're all non-clinical. The only way you can test to see whether that's a significant change in classification is by doing a test like this. Yep, so that's just why you use this type of test. Now, to do these tests, they basically indicate whether the likelihood of a binary outcome is differentially likely at different sampling points for the same people. So the Cochrane's Q test, which gives you a Q statistic, which we'll be doing these tomorrow, so you'll become more familiar with them, basically says people differ in their preference for ice cream. One type of ice cream is more popular than the other 2. It doesn't tell you which one is more popular. It just tells you there's a difference. A bit like an F test. 3 groups, the groups are different. So what you do is you do a McNemar's test, which is for 2 related samples. And that enables you then to compare time 1 and time 2. Is there a difference? Yes, there is. So my clinical practice is actually making a difference to clinical depression after 4 weeks, of 1 round. And then time 2 and time 3 are compared. And that's significant as well, which means that from time 2 to time 3 it makes even more difference. And what will happen therefore is time 3 will be different from time 1. So what you commonly do is you run the Cochrane's Q test first to find out is there a difference across time, and then you use the McNemar's test to compare individual time points. So one project I'm working on at the moment is this big longitudinal study in New South Wales. It's called the Pathways to Care project. And so we've got like 1,200 kids coming into foster care, and they're tracked over 5 years. We've got wave 1, 2 and 3. It's the biggest study ever was type, and the government's put a lot of money into it over there. And one measure we've got in there, for example, we've got the child behaviour checklist, which classifies people as clinically externalising behaviour, internalising behaviour, which is depression and anxiety. And so for every wave, I can see how many children are clinically depressed, or score in the clinical range for externalising and for internalising. And so for internalising, for example, I can then sort of do a Cochrane's Q test showing whether the percentage of children or the number of children who come up clinical is changing over time. So what we want to see, and I can compare it across kinship care too and see whether the pattern is different for kinship versus non-kinship care. But once I've shown that there is a difference between the waves, I then use the McNemar's test to see which of the waves there's a difference in the count of kids who are clinical. So that's how you use it. Now, what we'll be doing in the lab session tomorrow for this bit is that right at the end of the handout, the actual lecture notes, which sort of run parallel to the... Don't worry about all these sort of examples. It's just here to give you an illustration of what problems might look like. But the actual lab exercise is given right at the end. You see at the end you've got the SPSS exercise. All this data here I've made available to you in an Excel format. So I've reproduced all these tables in an Excel file. You open up the file tomorrow, you'll see Excel. And I think in the first tab, you'll have all the data like this for the different questions. You can just cut and paste it, chuck it straight into SPSS. The important thing is when you cut and paste, don't cut and paste the gender and just cut the numbers. Otherwise, it'll go can't compute, so something wrong because you've got the wrong type of data there. So you just basically select all the data and just cut into Excel. Cut from Excel into. So the first one you'll be looking at 40 students interviewed at random and asked whether they'd like to go for lunch, Noodle Bar, Macca's or Subway. It's a bit like there's choices at the hub at the moment. They're not as savoury as they could be. Best place is that pasta joint in Myers as you walk in, turn right. Yeah. $8, excellent pasta. Costs $11 at the bloody hub, yeah. No good. And Matt Dry and I scout around for good feed, so you get good Vietnamese food down the street. There's the chi-squared two-way example, and then there's an example of Fisher exact one, where you can see the numbers aren't very good; they're pretty small. The chi-square will be invalid, so you can run a Fisher exact test. And then there's a Kappa one. Got two raters. The data actually in Excel is all down the column, so you don't have to sort of run into any problems when you select it. But you can see two raters classifying people as suitable or unsuitable. So you can cut and paste and run a Kappa. And then we've got some examples where you can run Cochrane's Q and run McNemar's tests as well. So I've got a little SBS guide, and I've got all the data. And also I've got worked examples too, so you can actually work off the outputs to see you've got the right answer. So it takes you right through. So at the end of tomorrow, you'll be able to, be a bit more familiar with SBS if you hadn't used it before. You'll think, yeah, I can do this, it's not that hard. And then you'll know where to do some of these basic analyses. All right, so we'll take a break, maybe come back at about 1:45, and we'll do the logistic regression, which is, of course, the regression technique that uses binary data as the dependent measure. Now, I've got a handout for that, which I'll bring along for you this afternoon.
Oh,
Yes.
All right, guys, we'll make a resumption, and hopefully we'll be finished by 2:30, maybe. Yeah, or even earlier. Yep. All right. Okay, so the second part I want to talk about logistic regression. Obviously, you'll learn a bit more about it when we do the lab session tomorrow. So logistic regression is a technique I use a lot in research, and it's a very, very useful technique. Have anyone done logistic regression before and how to use it? Yeah, so most of what you've done so far would be standard multiple regression or linear regression, where the outcome measure is a metric variable, where it'll be something like you're predicting whether a person's depressed or stressed, where you're measuring it on a scale of some shape or form. What commonly happens in many research situations is that the outcome measure is a grouping variable, a binary variable. And when it's a simple binary variable, like this, you can conduct what's called binary long logistic regression, which essentially is working out the best predictors of whether someone belongs to a particular group. So, are you a smoker? Are you depressed? Are you a Port supporter? Manchester United. You try and find out, you try and predict that membership in the group. So the outcome measure is 0 or 1. And so the aim is to try and come up with an equation that predicts with the best probability whether you belong to the upper coded group. So it can be 1 or 2, it could be used as well, but you can use 0 and 1. So the outcome variable is a binary outcome variable, 0 or 1 or 1 or 2. And you're trying to predict membership in that higher group, the 1 or the 2, the one on the right. And essentially, the probability of being in that group is given by this formula here. This logistic formula, which is just the natural logarithm e, or e raised exponential raised to z, divided by 1 plus e to the z, where z is simply just like a normal regression equation, the linear combination of variables. So if you've measured gender, age, a whole range of things, you have a typical, standard regression equation. You've got the constant plus the parameter for gender times your value for gender, x1, plus might be age. You've got your parameter for age times your age in years, right through whatever variables you've got in your equation. So if you're familiar with multiple regression, you have an equation which predicts a particular outcome, and you have regression parameters or b values, which you multiply by the values of your predictors to get the predicted score for your dependent measure. So that bit, the z bit's the same. And so you essentially, the software will program, or it's programmed to calculate that equation, but it puts it into this formula here, which yields a probability. It says if you are, have various qualities, if your gender is this, your age is this, your socioeconomic status is this or something else, you're likely to go overseas 4 times in a decade. It might be something like some tourism type study. So you can use it like that. So you actually end up with a probability. You have that person with that profile has an 80% chance of being someone who goes overseas, say 4 times in a decade. In my line of research, the sort of things I do, this person has been spotted in a venue going to the ATM 3 times. This person has played 4 hours on the poker machine without leaving. This person was there when the venue started. I put those into the algorithm, and that person's got an 80% chance of being a problem gambler. So some of the work I do with the government, did some stuff with ACT last year, and I've done stuff with casinos where you have these algorithms. You basically have these profiles. You've done studies working out how probable certain things are in problem gamblers. We do some, and so if you can observe those signs, you can work out which people are people of interest. And the same thing is done with people who are in security environments. They have certain profiles they look for. It's in shoplifting studies. There's certain things they look for too. So the person who walks in and doesn't purchase anything, that's a warning sign. Second ones are looking at the cameras. One up there, I think, looking at us. 2, and then there's I think there's some third one too. And so that's how they then have algorithms and software which says, probability of this person being a shoplifter is elevated. Watch that person. Same thing's done with insurance risk and those sorts of things. They plug in all these sort of different figures from your information you provide. They give you a figure which indicates your risk of being an insurance risk or car crash risk and those sorts of things. So these sorts of probability-based calculations, maximum likelihood rather than using standard regression, quite commonly used in a number of different applications. I use it in the child protection field to work out which kids are most likely to be unstable when they go into care, or if they are most likely to be at risk of abuse. Michael Provey and I are doing work on looking at whether you can profile people who come in to work with children who might be at risk for people. You can't sort of study it very easily, you don't want anything bad to happen, but a similar sort of statistic will be used. So that's the basic mechanics. Now, what you get from logistic regression is a table like this. So the first bit looks a little bit like a normal regression. You've got the actual parameter values. So these are the ones. These are like the B values. These are not the standardised betas, which we'll talk about next week. These are the parameters for the equation which go into the calculating the overall linear equation. And so they're very similar. This one here, the Wald statistic, is a bit like a t-test. It's like a statistical test that determines whether these variables, these predictors, are significant predictors in your equation. So just like a normal multiple regression, you have a series of predictive variables, and you have a t-test to tell you which ones are actually significant predictors of your outcome. The Wald statistic fulfills the same purpose. So the first thing you look for, which of my predictors are significant, and you look for a significant p-value with your Wald statistic. And you can see here there's two variables here, the less than 0.05, which are significant predictors of the outcome. Now the other thing, the most important statistic in logistic regression, which is different, is in SPSS it's called the exponent b, but it's actually it's called the odds ratio, or OR. Now, once you understand the logic of the odds ratio and the logistic regression, the whole thing makes sense. So the basic idea is this. Every predictive variable will be given an odds ratio. So for example, 3.42, the value which means absolutely nothing, you've got no effect, is 1.0. That means 1.0 is chance, nothing. It means that the probability of the variable makes no difference. So if your 95% confidence interval here, which you have here quite often, contains 1, that means your predictor is not significant. It will actually not be significant. So here, we've got a significant effect for gender. Now, gender is most commonly coded male equals 1, female equals 2. For some reason, that's a convention. We say ladies and gentlemen, but we always do the male and female in the coding. 1, 2. And so an increase in gender means usually going from male to female. So that's the only one unit change you can make. You're looking at binary gender. So 3.42 means that if you go from a 1 unit increase in gender, that is going from male to female, is associated with a 3.42 times greater probability of being the person who goes overseas or the person who has some other quality. So that's how you interpret an odds ratio. So this one here, for example, each unit increase in age is associated with a 21% greater probability of being in that group. Now, SES is not significant here, but if it were, that means that every unit increase in SES is associated with an 86% greater probability of being in this group, being a smoker, if that's what you're looking for. Another way you can say is the probability is 1.86 times greater when you have a unit increase in SES. Another way of putting it again is to say that the odds of being in that group are 1.86 times greater when you go up 1 unit on SES. That's how you interpret these things. Now, the way in which it works is as follows. Let's imagine gender is your predictor variable, and you've just calculated the probability of people going overseas, and it might be, say, 30%. Or let's say it's 20%. You then go in here, and you've got male as your gender. Let's change gender to female by changing that to a 2. You bump up a unit change. Up it goes. You recalculate the Z-score with now gender added in as a 2, and you pop it back into the equation. The probability will go up 3.86 times. It'll go up to like 90%. So you can see a unit increase in gender increases the odds calculated through this for being that by 3.86 times. That's how it works. So that's the basic mechanics of logistic regression. The odds ratio means that the probability of being in that higher group goes up by that amount. Or formally you say the odds have gone up by 3.86 the same. You don't want to confuse it with a relative risk ratio, which is really just how much, say, females do something versus males, which can be a little bit different. So that's the basic mechanics of this logistic regression. So when you run this analysis, your dependent measure will be a binary outcome, 0 or 1, smokers or non-smokers, 0 and 1 column of outcome variables. And then you've got your predictive variables in different columns, and so you go into logistic regression, you put in your predictive variable, your outcome variable, your binary variable, then you put in your predictors, and you run it, and you get the output like you've got there. Now, the first thing you look at before you get to the table, you might recall in standard multiple regression, you have the R-squared value, which tells you how much variance is being explained by your model. It tells you how exciting your model is and whether it's worth running. The equivalent in this type of maximum likelihood estimation, or these types of probabilistic models, is what's called the percentage of cases correctly classified. So when you run a logistic regression, you have a little statistic called the percentage of cases correctly classified, which will become clear when you do it tomorrow. Not sure if I've got that here on that in the handout. So doesn't matter. So the basic idea of that is that, let's say, for example, I was doing a child protection study and I wanted to know if a child, I was doing a model to see which children get abused in care or something like that, something not very pleasant. I already know from my data how many kids were abused in care. So I know what this total is here. I know exactly how many there were. But what the logistic regression does is calculate a model which assigns probabilities to each child based on certain predictive variables and then puts them into the groups. Now, in a perfect world, you'll get every single one correct. Let's say, for example, you had 100 children and 20 were abused. Not that happens. It wouldn't be like that. The perfect solution will look like that. Actual was 20, and the model exactly predicts and correctly classifies 100% correctly. In other words, the model is so good that when you put in the characteristics, it's this particular child, it says, nah, probability is really low, that child's predicted to be less than 50%, go on that group. A child who's got certain other characteristics in combination, very confident it's in that group. That's a great model, 100%. A chance model is 50%. So a really good models in real life will be, say, 70 or 80%. If you get 70 or 80% classified correctly, then you'll be very happy. And so what typically the data will look like will be more like this. You won't get, for 100 cases or something like this, you'll get, say, 10, 65, then you might get, say, 15, 25, 8, 10. So it might look something like that. And so the percentage of cases classified or correctly classified is a bit like your R-squared. You want to get a figure of at least, say, 70, 80% to be really happy with your model. Yep. I think the one tomorrow is fairly average, pretty mediocre example we use. So that's the first thing you look for, a bit like looking for your R-squared when you're doing your thesis and saying, oh, how big's my R-squared? And then you go and say, okay, which variables are significant predictors? And that's where you go to the wild statistic and go, okay, I've got two variables which are significant in my model. What commonly you do when you run logistic regression is you say, right, this one here is not significant, it's a bit redundant, so I rerun my model just for the significant ones. That's what you commonly do. So often you'll run, in fact, a lot of statisticians, what they'll do is they'll use chi-squared and univariate test to work out like a set of variables they're going to put into the final multivariate model. And sometimes they even do it based upon probability of less than 0.1 rather than 0.05. So they come up with a set of, say, 10, 15 variables. They chuck them into this model like this. Okay, 8 have come up significant. Right, I'm going to dump the other ones which aren't of any use. And you come up with a model which is only based upon significant predictors. And then you can then use that to do useful things. And so the next thing you then look at is the odds ratio. Now, the odds ratio is not quite like an effect size because if the variable is something like gender, there is usually only one unit change you can make. You're basically going male or female. There's no other change. Whereas with age, each unit change in years is not very exciting. So the odds ratios for age measured in years are usually very small because 1 year of age change is not very exciting, doesn't make a lot of difference. Whereas 1 unit change in gender is a complete change in gender. So the odds ratios are always bigger for gender simply because of the way it's scored. You only get comparability in the comparison of odds ratios when both variables are binary. So, for example, if I was having as predictors, say, emotional abuse, physical abuse, sexual abuse, all three were scored 0-1, 0-1, 0-1 as predictors, then I could compare the odds ratios and say that one's more important than the other one, because they're all binary. There is only one change, 0-1, 0-1, meaning it occurred or it didn't occur. So that's basically how you do it. So you report the number of cases classified, my model's pretty good, and then you go through and indicate which variables came up as significant, and then you can talk about how to interpret those findings. And so you go through, okay, each unit increase in age and years is associated with a 1.21 greater odds of being in the group of interest. Being female is associated with 3.42 greater odds of being in the group of interest, and so on. That's how you write up a logistic regression analysis. These things are very useful because what you can do is once you've come up with a series of predictors, this was what I did with this gambling profiling type study and also in child protection studies, is you can sort of profile people. So for example, let's say for example people come in and you're looking at the risk of, you'll see in many conferences people looking at say cancer risk and things like that. They will say, well, a person comes in with a series of risk factors. Being over 50 is a risk increases your risk of cancer. Being a smoker, yes or no, increases your risk. Parental history is a major factor. And so a person might walk in whose only risk factor is the person's is above 50, but not a smoker. Although this person's got parental cancer history, this one here's got just age. Some people come in with all three. So what you can do, of course, once you've got an equation that predicts cancer based upon age, smoking status, and parental history, of course you can have a lot more variables than that, you can then say, right, well, what's the probability of cancer for a person with one of those things, two of those things, or all three? And so you'll see doctors and medical researchers often putting up diagrams look like this, where they give a probability in the middle, which is where the variables, all three of them have a 1 for the risk factor being present. This one here might be for only B being present. This probability here is only C present, only A present. This one here is for A and B being present. So you can see once you've got your equation, you can just vary the predictors that come in and then use it to profile. So imagine if you're working in a security environment, working in a casino running algorithms, okay, who's a problem gambler, and you've got certain signs observed. And that's what they do with tracking studies, big data studies. They analyse patterns of behaviour, and then they put in the algorithm that's calculated, and it says, right, this person's got like a 70% chance of being such and such. This is a person of interest. And so they do the same thing. Of course, Google's doing all this stuff all the time. They're basically calculating based upon what you've done before, what you looked at. They work out people who tend to do that tend to do this because of a very high probability because of what we've seen before in the patterns of behaviour. And so that's how these types of models are used widely in more advanced forms in machine learning and big data analysis. So tomorrow, after you've done the first basic tests of like chi-squared and so on, we'll get you to do a logistic regression analysis, and the actual exercise is here. The data set for it is I think it's on tab 2 of the Excel file. So you just cut and paste in the data to SPSS, and then we're looking at what predicts being neglected in care. And so you've got gender, parental substance abuse, present or not present. Actually, what was it now? What's the predictor again? Oh, it is neglect, that's right, yeah. So you've got substance abuse and gender as the two predictors, and then you're just basically putting in the two predictors and then interpreting the results of the logistic regression. And also you can have a go at calculating the probability of being neglected if you have both of the risk factors present. Your calculator probably won't have the ability to do it, but I've got the calculation there. If you've got bring a calculator tomorrow if you're coming into to the lab, because you'll be able to do it. Or pick one up from sort of Handy Mart somewhere. You can get those $5 ones which can do all the tricks. So by tomorrow, you'll be able to run a logistic regression and interpret it, and hopefully see why it's useful. So, any questions about logistic? Yeah. No? Right, I'll keep my promise. Yeah, 2:15, so we're done for the day, and so tomorrow, we'll I'll see you over at the labs 10 o'clock, I think. Yeah. So start whenever you like, and then I'll be in there at 10. Yeah. Yeah. There we are. Oh my god. Oh bugger. I didn't record it. Oh. Oh, this is my mother. Oh, it's your mother. Means that when you do the calculate, you've got 6 cells. So you can calculate the minimum frequencies, column totals, round totals, you've got 6, so if you had like 4 of those calculations, they came up, they came out 5, less than 5, then you have 4 out of 6, or 2/3 of your cells, and then the expected frequency less than 5. Yeah. So again, so if you had, so here we do, if I do 180 divided by 290 times 90, that would be quite big, fine. I'll do it again. All these are going to come out fine. They're going to be quite big numbers when I do the expected frequency calculation. Yeah. So just imagine that was like only 18 or 11, and that was 29. And if you do that, you'll find most of it will come out less than 5. Yeah, and more than 25% of those cells come out that way. Which, so for example, with 6, you only need like 2 come out less than 5. That's 1/3 already gone. You will use those squares.
Okay.
Yeah.
But if I made some numbers with less than 25%, I would do like other tests, right?
Well, you can combine the cells. So a common example is things like this. Let's say you've got Canada, US, UK, Australia.
But Friday suits you. Friday is actually, I'm going to be trying to lunch.
No, yes. And you go. Sorry. You go and you calculate and you go, oh, I'm getting problems with these cells here, the numbers are really small. What you can just do is go North America, put these together and make it 15 and this versus 14. Collapse the cells and the same thing, yes, except it becomes a 3 by, it goes from being a 4 by 2 design to a 3 by 2 design. So that one comes together. And that way you end up with no small.
Do you use Facebook like Sarah?
So when you calculate the, so you calculate the expected frequencies in the cells, that's the third thing. Let's say that the expected frequency is 8. That's pretty close. If let's say, for example, you had like a 2.
Like on our way, no, comes this way.
Standard residual basically takes that difference. That was 2. That will be a huge amount that will come up to make the chi-square bigger. And so standard residual is standardises those differences. It standardises the differences between that value and the expected frequency values for each cell. And so where the difference is very big, you probably would get a value above 2.
Okay.
Which means that cell is really, really important, which means people from Canada really hate, or people in the US seem to like Trump more than other people in the or something like that.
I remember in my research in undergraduate, I suppose it will automatically give you like standard residual.
It does. You just ask for it as an option, and it does it for you.
Yeah, okay.
Yes.
Yeah.
That's all right. Yeah.
Well, I don't actually question about statistics.
Yes,
I was actually about behaviour resilience.
Yes, that's all right. Yeah.
Just because we're doing that across mind, brain, and behaviour,
Yeah.
so where does mind come from? And from a cognitive perspective, but from the from a behaviourist perspective,
Yep.
is it too reductive to say that the behaviourist view is that human behaviour is reactive? To me, it just seems like it's reactive. You behave in reaction to your environment, but is that too reductive a view of behaviourism?
Behaviourists, behaviourists have both a there's different types of behaviourism. So the classical, it's called radical behaviourism, essentially says yes, stuff goes on inside the head, but from a practical point of view, I don't need to know about it. So essentially, when I'm studying what people buy in the shop, I don't have to worry about going and survey you and ask what sort of, what's your cultural background, what type of food you like, what are your allergies and so on. I just basically just watch what people do, and that does very well in working out whether putting food in a certain place, pricey in a certain way, leads to a certain outcome. I don't need to worry about what's going on inside people's brains.
What the motivation
That's
is for
right.
going to those places.
Yeah, and so all the stuff I was just talking about before with behavioural patterns online, all that's done largely through just plotting what people do. The best predictor of what a person's going to do is what other things they do, what they've done in the past. And so all big data type profiling analyses show that you can basically don't even know anything about these people, you can pretty much learn everything about them just by what they do. You don't need to overthink motivation and everything else. And so the behavioural view is that you don't need to go inside the mind. However, there are obviously neural network and computational models which are essentially behavioural in nature as well, which come up with ways to try and study how we might think, but where the models actually learn. And in a sense, those models are forms of learning models. So one way is the idea the mind's certainly in there, but we don't need to worry about it to study behaviour or get reasonable prediction. Whereas neural network type stuff say, well, we think people's memory probably works like this, and so we can train a model to sort of emulate what people do and how they think. And so in a sense, that's a form of learning algorithm as well.
So the pure behaviourist sort of approach is a bit more like a constructionist kind of approach, because he says we're not trying to get in the mind, we're just looking at how people create, how we create meaning out there in the world rather than in here. All right.
I'm sure this thing is done. It's got 40 minutes. Oh, it's remaining, isn't it? Yeah. I think it's actually continuing right
Have
through.
you turned your thing off?
Yeah, I did.
We don't want to
Yeah.
All right, thank you. Does that make sense? Yeah, so it's not about what goes on in here. But you do, because there is like Skinner and all that, looking at learning. So obviously must have thought something was going on in the brain.
It just basically says you don't need to study it. From a functional point of view, you can pretty much know everything based upon what goes in and looking at what goes out. So what's inside is all fusing, too complex and fusing. You pretty much have a pretty good lever on what's happening on the world by just looking at the inputs and the outputs.
Great, thanks very much.
That's all right.
See you tomorrow.
Tomorrow's tough for you, run around like a madman.
as much